Okay, so welcome back. So our plenary speaker today is Jeremy Teitelbaum, who had been a dean here for a long time and has just returned to being an ordinary math professor. So he's going to tell us today about how you can factor with elliptic curves.
All right, thanks, Keith. Hi, everybody. Good to be here. So this is going to be a quick overview of Lenstra's elliptic curve factoring method, which is kind of old at this point. The paper was published in '87. So, but it is a very fundamental piece of the computational number theory toolkit. So I think it's worth looking at how it works. And since it does take advantage of elliptic curves, and I know there's a course on elliptic curves, it seems like an appropriate topic for this meeting. So the problem that we have is that we're given a composite positive integer n, and we want to find a prime divisor of it. This isn't exactly the same as factoring it, because for the moment we'll be happy if we can find one proper prime divisor, and we may end up with a number which has other factors that we can't then further factor, but one step at a time. So, the method you learn in grade school is that you start trying numbers. If you're a little bit more sophisticated, you try prime numbers, and you try to divide your number by each prime number in turn. And you stop when you reach the square root of the number, and you either find a factor or you don't. And if you do find a factor, then you're happy. And if you don't find a factor, then you're also happy because you've proved that the number's prime. But if you think about this algorithm, I mean, we routinely nowadays talk about 50, 80, 100-digit numbers. And if you think about a 100-digit number, that's 10 to the 100th. So just as a little quick calculation, if you can do 10 to the 12th divisions per second on some computer, and that number is totally irrelevant, pick any number that you want, then to do a 100-digit number would take 10 to the 38th seconds, which is about 10 to the 30th years, which is many, many, many orders of magnitude greater than the age of the universe, for example. So to reach numbers of any sort of respectable size, you need a different approach. And there are really two types of factoring algorithms that are in use today. One kind takes advantage of what I'm calling algebraic groups, and the other kind is based on what are called sieve methods. And so the elliptic curve method is an example of an algebraic group type method. The P-1 method, which I'm going to use as an example, is a type of an algebraic group method. You may know about or have learned about the quadratic sieve or the number field sieve. These are sieve methods. The thing that distinguishes them is that algebraic group methods their running time tends to depend on the size of the smallest prime factor of the number. So they are good at finding the relatively small prime factors of a number. Sieve methods are blind to the size of the factors of the number. They take just as long to find, 7 as a factor of some huge number as they would to factor a number into two 80-digit primes. So in practice, what you do is you use an algebraic group method to rule out small prime factors. First you do trial division, then you do an algebraic group method. Then the number that's left, you apply one of these sieve methods to. They are they're typically done in a distributed set, on many computers, and it's kind of a big production. So as I mentioned, typically you use an algebraic group method to find the small factors of your number, and then when you are ready, you use a sieve method. These algorithms are what's called sub-exponential time. So in factoring exponential time, the relevant variable is the number of digits, the logarithm of the number. So exponential time means exponential in the number of digits, which is exponential in the logarithm of n, which means more or less a power of n. Those are bad. Sub-exponential means anything better than that. And so the elliptic curve method is better than exponential time, but far from polynomial time, which is kind of the dream. the true complexity of factoring isn't known, and even the theorems in this field depend on a lot of unproven conjectures in analytic number theory. But there is a quantum algorithm, which is polynomial time, about which I know nothing. So the first thing that you do if you want to factor a number is that you make sure that it is composite. And this is fortunately easy to do in practice. You apply Fermat's theorem, the easy Fermat's theorem, or the small Fermat's theorem. So you have your number n that you want to know if it's composite, and you try to compute a to the n minus 1 mod n. And hope that you don't get 1. Because if you don't get 1 mod n, then you know that your number can't be prime. I'm assuming that we've ruled out any factors of 2. So if you try this, and if you do happen to get 1, if a to the n minus 1 is 1 mod n, then n is called a pseudoprime to base a. And these happen, but they're rare. So if you're into this kind of trivia, there are 21,853 base 2 pseudoprimes less than 25 billion. And if you try a few Fermat tests, you can almost always show that your number is composite. And you can refine this a little bit. I mean, the moral of the story is if you can't, with a relatively limited amount of effort, prove that your number is composite, you should reconsider your plan for factoring it and think instead about possibly proving that it's prime. And I think this comes up in the, Keith talked about the Mersenne numbers, and you see that strategy applied there. Now, all of these algorithms require that you can compute the mod, you can raise a to the n, x mod n efficiently. And the naive way to do that would be to take a and multiply it times itself x times and reduce mod n each step. But then you're immediately out of luck because that's going to require n multiplications and x multiplications, but x is a random number tantamount to being of size n. So this amounts to doing n multiplications, so you're obviously not going to get anywhere. But there's a very simple way to do exponentiation, which is log of logarithmic time. And I don't know how many, maybe everybody has seen this. It's very elementary. But if you haven't seen it, you should know it. So I've written the algorithm down here. We want to compute a to the x mod n. And so I've written the algorithm down a little bit. The idea in this algorithm is that we, instead of multiplying, we square. So we keep a running accumulation of, we square a, and then we square that again, and then we square that again, and so we get a squared, and then a to the 4th, and then a to the 16th, and then a to the 32nd, and so forth. And we know that x, the exponent, can be written as a linear combination of these powers of 2. It's basically the base 2 expansion of x. And so we can combine these repeated squarings of a to get x. And this is an efficient way to do it. And just to show you, I think I have a little example here. So here I want to compute 5 to the 123rd power mod this random number, 123,199. And in the right-hand column, I've written the exponent in binary. And in the middle column, I have, what have I got? In the middle column, I have the square. I start with 5, and I start squaring 5, mod 123,199. So I get 5, 25, 625. I'm reducing mod n at each step, so at some point you stop recognizing them as powers of 5, but they are. And then in the left-hand column is what happens. So you see if the binary digit, if the ones digit of the binary expansion of x is 1, then I multiply the middle column into the left-hand column and reduce mod n and square the middle column. Then I shift over by 1. If the column is in the next row, you see I have another 1, so I multiply the 5 by 25 and I shift over by 1. Now I have a 0, so I don't multiply the middle column over. I just carry it down a row and I square the middle column again. And I keep doing this, and if you think about what I'm doing, I'm using the power, the a to the 2 to the n to reconstruct x in binary and raise m, or raise a to that power. So this takes time log base 2 of the exponent. You can actually be cleverer than this, and there's a long discussion of this, a very old and long discussion of this in Knuth's Art of Computer Programming, where for particular exponents you can choose extremely clever systems, but this is good enough for us. So you can exponentiate efficiently mod n. So the elliptic curve algorithm is modeled on an algorithm due to Pollard, although the idea is extremely simple. There are many algorithms due to Pollard where the idea is extremely simple, but he was the first one to think of actually doing it, which is to factor. And it's the prototypical example of an algebraic group method. And the idea is basically to think about the Chinese remainder theorem. So we want to look at we have some n that we know is composite, and we look at the multiplicative group of units mod n. Well, n factors, right? So that z mod mz is really a z mod az times a z mod bz. So it's certainly not cyclic. So this multiplicative group is certainly not cyclic. It has two factors, at least. And if you forget about 2, in principle, it's really just a non-trivial product of cyclic groups, but that doesn't even matter. What we do is we pick a base, and we try to find an exponent m with the property that a to the m is going to be 1 modulo one of the factors, but not the other. So, for example, if our number were p times q, and if n were p times q, and we raised a to the p minus first power, that's going to be congruent to 1 mod p, but unless something weird has happened, not mod q. So when we take a to the p minus 1 and subtract 1 from it, it's divisible by p, but not by q. And now we take the greatest common divisor, and we find with n, and we find p. So this is wonderful, except for one problem, which is, of course, we don't know the factors. Okay? So we don't, and the thing that we care about is n has a prime factor p and a prime factor q. It's p minus 1 that we care about for one of those factors. We have no idea what that is. And so we just try to guess it, basically. So we pick numbers, and we raise them to this power, and we hope that this m is a multiple of p minus 1, where p is one of the divisors of n, but not q minus 1 for one of the other divisors of n. That's kind of the strategy. How does this have any hope of working? Well, the underlying idea is what's called smoothness. So smoothness for numbers mean a number's smooth if it's a product of a lot of small prime numbers, given its size. Okay? So like 2 to the 50th is a very large number, but it's very smooth because all of its prime divisors are small. They're namely 2. Classic examples of smooth numbers are factorials, right? Like 50 factorial has all its prime divisors left at less than 50, even though it's an enormous number. So, and I give you 41 factorial there. And actually what we care about is not just that the numbers are smooth, meaning that they're a product of small primes, but that the powers aren't too large. They're a product of relative, so you basically want to say that the number has no prime divisor bigger than something, and none of the prime powers, none of the exponents are any worse than something else. And those are the kind of numbers that we're interested in. They're called power smooth. Okay? And so the p minus 1 method hopes that not only does n factor as p times q, but one of its factors has the property that p minus 1, this is this unknown factor, so we're taking an unknown factor of n, which is prime, and now we're looking at p minus 1 for that unknown factor, and we're hoping that that is a smooth number. that p minus 1, by some miracle, happens to be a product of a lot of small primes, not to very big powers. And if that's the case, we can take numbers m, which are cooked up to be products of small primes to relatively small powers, and hope that the p minus 1 that we're hoping to find divides that number, which isn't too big. So we try such m's, and we hope that a to the m minus 1 is going to have a factor in common with n. So this will happen if m is one of these power smooth numbers, and if p is this unknown prime divisor of n, p minus 1 is a product of small primes to relatively small powers. That p minus 1 is going to divide this m. I should have used a different p, because this p in this product is not the p that we're interested in. These are other small primes. And maybe this works. And if it does, you find a factorization of n. If it doesn't, you can try a bigger b, or you could try a different a. So here's an example. Not very scientifically done. So the fifth Fermat number is 2 to the 32nd plus 1. We're going to try to factor it by the p minus 1 method. And 2 is a poor choice of base. But let's take 5 for no particular reason. And take m to be 10 factorial. And compute 5 to the m minus 1 mod this big number, which you can do efficiently. 10 factorial actually isn't that big a number. And you get this ridiculous number, and you take its greatest common divisor with F5, and you find 641. Why did this work? Well, 640, I will point out to you, is 164 times 10. So it's 128 times 5. So it's 2 to the 7th times 5. Okay? So the fifth Fermat number is divisible by 641, and 641 minus 1, which is 640, all of its prime divisors are at most 5. So that's a perfect situation for the p minus 1 method. If you're feeling adventurous, you could try, I think I have this here. You could try a bigger, can you see this? So you might try the 128th Fermat number, okay? And you could raise 3 to the 200 factorial, okay? And subtract 1 from that, you get this big number here. This is 3 to the 200 factorial modulo the 2 to the 128th plus 1. Subtract 1 from that. And now you take the GCD with your Fermat number, and this is the extended GCD. So the first number is the greatest common divisor, and it's 1, so you were out of luck. Okay, so you think, well, that's silly. Let's try 500 factorial. So what we're guessing here is that if this 2 to the 128th plus 1 has a prime number, prime divisor, is it possible that p minus 1 for that divisor has sort of all of its primes divisors of that less than 500? You might try that. But that doesn't work either. And you could keep trying this, and actually it's not going to work. Because, as we'll see later, this smoothness condition doesn't hold. You would need to try a very large. In order to get, this number is composite, but its prime divisors aren't very smooth. When you subtract 1 from them, they have big prime factors. So you're unlikely to find it by the p minus 1 method. So the bad thing about the p minus 1 method is if it doesn't work, namely if it isn't the case that your number n has a prime divisor p, so that p minus 1 happens to be smooth, then there's nothing else to do. You're out of luck. And that was the state of the art in the 70s for the p minus 1. Actually, I shouldn't quite say that. You can also do the p plus 1 method, which uses the algebraic group, which is the multiplicative group of units whose norm is 1 in a quadratic extension field. There's other tricks. But there were only finally many such examples. And then Hendrik Lenstra came onto the scene. His paper was published in Annals, which is unusual for a paper about computational number theory. And it was published in Annals because it was the first factoring algorithm that, within the sort of what counts as provable in this field, meaning accepting the usual sort of hypotheses about the distribution of smooth numbers, and a few other conjectures that, that people were willing, that this was the first provably sub-exponential general purpose factoring algorithm. Okay, and it has the property that its running time is, and I'll explain this a little bit later, is depends on the smallest prime factor of p, and it is incredibly effective in practice. Okay, so it is when you type, when you ask Maple or Mathematica or Wolfram Alpha or one of these or Sage to factor an integer, it's the elliptic curve method. And we'll see this in a minute. And it's actually shockingly simple to implement, but it was a brilliant insight. So how does the elliptic curve method work? Well, it's the same idea as the p-1 method. Namely, we have our n, which is composite, and so it factors as u and v. And now we look at our elliptic curve, and we look at its points mod n. Yes?
Are you first going to check that it's not a prime power, for which you can't do that?
Yes, okay. You should do a few preliminary checks. You should run trial division on this. You should rule out the case that it's a prime power. That's doable because if it is, first of all, there is a linear time algorithm to verify that it's a prime power or not due to Bernstein and I think it's due to Bernstein maybe. But you can also rule out a prime power in practice because if it is a prime power, the number that it's a power of has to be pretty small if the power is in. So you can check it's not a perfect square. Take its square root. Use analytic methods, in other words. Take its cube root. Pretty quickly you rule out prime powers. Okay. So now we have this n, and we know it's composite, and we look at the group of points mod n on the elliptic curve. So what does this mean? It means that, it has a formal meaning in algebraic geometry, but for the moment, what it means is we're just going to pretend that n is prime, and we're going to look at coordinates in a standard Weierstrass model for our elliptic curve, and think of them, that we can add them by the usual formulas where you take the line and do the usual stuff. Now, what are we hoping for? We're hoping that we can find a point P on the curve mod n with the property that some multiple of it is 0 in the first factor, but not the second. Okay? So what would that mean? It would mean you start out, you have your prime P on the elliptic, point P on the elliptic curve, and you start doing the formulas for multiplying it by some number. And at some point, when you do this, something goes wrong. What happens is you have to do a modular inverse. If you think about the formulas for the addition on elliptic curves, you have to do sort of y1 minus y2 over x1 minus x2. And you have to do that mod n. And if x1 minus x2 is not invertible mod n, you're happy. You have found a factor mod n. And that's basically the idea, is you try to multiply p and hope that something goes wrong. And what's going to go wrong is that the z-coordinate is going to become not relatively prime to n, so you can't invert it. And not relatively prime to n means it has a factor in common with n, and that's what you're looking for. Now, there's a very simple idea, and you see the comparison with the p-1 method. Yeah?
How do you choose your elliptic curve or what?
Okay, I'll get to that. Now, when is this going to work? It's going to work if the order of the group of points on the elliptic curve mod u is smooth. Okay, because if that were the case, then in the p-1 method, we take a to some power m. Here we're going to take our point p and we're going to multiply it by m. If the order of the group is smooth and m is made up of small prime powers, then we have a hope that m times p is going to be 0 in the group. And we know quite a lot about the orders of the group of points on an elliptic curve mod p. In particular, we know that they have order roughly p. Right? That's the Riemann hypothesis for elliptic curves. And so what we could hope is that if you look at the orders of elliptic curves mod p, there are a bunch of numbers, as you consider all possible elliptic curves mod p, you could hope that their orders are just as likely to be smooth as any other number of that size. Okay? Now, that's an hopelessly unprovable statement in analytic number theory, but it's an extremely reasonable hypothesis to make. So we're going to assume that the numbers that you get as orders of groups of points on elliptic curves mod p, where p is large, are just as likely to be smooth as any other number of that size. And then the difference between the elliptic curve method and the p-1 method is, well, with the p-1 method, if your n had a prime factor p and p-1 wasn't smooth, you were done. But now if you have n and you have an elliptic curve n, and the order of that elliptic curve is not smooth mod p, there are other elliptic curves, many other elliptic curves. So you have a recourse. You can keep trying with lots and lots and lots of elliptic curves, hoping that you're going to get an elliptic curve where the order of the points mod p turn out to be smooth. So here's an example. This is our favorite example that I tried before, the seventh Fermat number, which is pretty sizable. And it's pretty easy to check that it's composite. So what do? So you asked, how do you get an elliptic curve which works? Well, let me see if I can skip ahead a little bit and show you how you do that. So I'm going to come back to this slide, but the way you do it, look at line 2 there and forget about the rest of the stuff. We have a number n. Just pick 3 random numbers, a, x0, and y0, and define b to be y0 squared minus x0 cubed minus a0 ax0. And now make the elliptic curve y squared equals x cubed plus ax plus b. x0 and y0 are a point on that elliptic curve. Okay? So that's how you do it. You could be even less random, and you could just say, I'm going to take b equals 1. I'm going to pick a starting at, let's say, negative 100 and going to positive 100. And I just choose my point to be the origin, x equals 0, y equals 1. So that's what I did for this example here. So this obviously has, sorry. Yeah, we're trying to do this. This is what we're trying to do. So the curve y squared equals x cubed plus ax plus 1, if x is 0 and y is 1, that's a point for any a. Okay, so we don't really care much about this elliptic curve because we're going to try it, and if it works for us, we're going to keep it, and if it doesn't, we're going to throw it away. And we can pick integers, let's say, between minus 100 and 100, and for not particularly scientific reasons, I picked b equals 10,000, and I took a number, b4, which is the product of all the primes up to 10,000, where the exponent, where the prime power is actually less than 10,000. So log of 10,000 over log of p is the power that you can raise p to get less than 10,000. Okay? So this is a big number. I could have taken factorials. It doesn't really matter. And I compute b4 of p using the elliptic curve addition formulas. And when I have to, so this b4 is quite a hefty number, but I use the same idea that I used for modular exponentiation to compute it. That is, instead of squaring and multiplying, I use doubling and adding in the group of the elliptic curve. So I keep track of 2 points. 1 point I double, and then double again, and then double again. The other point I add in the powers. Exactly the same algorithm as I used before, so that makes the multiplication logarithmic time. And actually, when I first wrote this, I wrote a little program to do this in Python, I knew I'd factored the number when my Euclidean algorithm inversion crashed. The sign that I had found as 0 was, I got an exception, arithmetic error, because in the addition formulas, when you compute, there's 2 things. In the addition formula, you compute 1 over x1 minus, the slope of the line is y1 minus y2 over x1 minus x2 mod n. When you compute x1, 1 over x1 minus x2 mod n, if x1 minus x2 has a factor in common with n, you get a crash. And that was, I cleaned it up since then. Or in the doubling, you divide by y. And it's the same thing. So you just keep an eye out for those. Yeah.
If n is some huge modulus, how difficult is it for the computer to do modular inversion?
Well, so that's trivial. It's pretty trivial, actually. So, I mean, depends what you mean by large. I mean,
Like
so.
the one you have here.
Oh, this is trivial. In fact, I'll do it for you right now. So here's a little piece of, here's the code. You'll notice that the entire elliptic curve algorithm fits on a screen there. And I did cheat a tiny amount in this because I used a library package to do the extended Euclidean algorithm, because that's the thing you have to do fast if you want this to work. And I could write it in Python, but for the sake of demonstration, I thought it would. So let's run this. So if you look at the bottom, it's trying to factor the 7th Fermat number, the 8th Fermat number, and the 9th Fermat number. So you see it already did F7. That was the one that the P-1 method couldn't do. And it's going to think about the others for a while, I think. Is it still running? Anyway, I think it... Oh, no, it didn't. Why did it not print the other ones? Well, anyway, it was mainly the F7 that I was interested in. And so it found this factor, I think. I've lost track of it, but you did see it there for a moment. This is the problem with computers. Let's try one more time, because I wanted that factor, although I think it's have it on this slide. Oh yeah, so there we go, and it finds this factor. And if you look at these two factors, and you subtract one from them, the first one has a 15-digit prime factor, and the second one has a 12-digit prime factor. So the P-1 method is going to have trouble finding them. Okay, you'd have to go all the way out to a trillion or something before you would find the prime factor that you need to get this by the P-1 method. Well, that's F7. I think it's still running on the other ones. So how do you understand why this works? Okay, and so this is sort of a statement of the algorithm that is the way Lenstra analyzed it. And there's various parameters that you have to choose. Okay, so you start by choosing what integers v and w. Okay, so what are v and w? So w is the bound on the prime divisors of the order of the group that you're willing to tolerate. Okay, it's the smoothness bound, if you like. And v is the kind of size of the prime that you might be willing to look for. Okay, so from that you cook up this number k, which is the multiple of the point that you're going to take. In the P-1 method, this was like the m that you're going to do. Then you pick 3 random numbers, as I explained, and you get a more or less random elliptic curve, mod n, with a point on it. And you start computing kp. Okay, one of two things happens. You compute kp, and nothing goes wrong. So in that case, you failed, and you try again. Or you find a divisor. So what choices do you have to make if you're going to do this? Well, first of all, you have to choose the smoothness bound. How many small primes are you willing to allow into the divisor of the order of your elliptic curve mod its smallest prime divisor? How big do you think that smallest prime divisor is? And how many times are you willing to try? Those are basically the parameters that go into this. Obviously, the bigger you set the smoothness bound, the more likely you are to find a factor, but the longer it's going to take to run. So this is the thing that Lenstra had to analyze. Let's just see. So this finished. I don't know if you can see that. So it found factors of F7, F8, and F9. Some of these were known. The small prime factor of F9 was known prior. Kind of a rule of thumb is the elliptic curve is very good at numbers up to 20, 25 digits. Elliptic curve method, very effective in that range. Not in Python, by the way. You should write it in a real language, but okay. So how do you analyze this? Well, you have to ask yourself very carefully, what's going to go wrong? What's the what is it that you're hoping is going to happen? So remember the algorithm. First of all, the V that you have to have chosen a V bigger, at least as big, as the prime divisor that you're trying to find. Okay? That's the first thing. Because otherwise, you might not look far enough to have any hope of finding a point that's going to give you 0. The elliptic curve that you chose had better be non-singular mod P. Interestingly enough, if it's singular, then you are basically doing either the P-1 method or the P+1 method, depending on whether the elliptic curve has split or non-split multiplicative reduction mod, whichever prime it is that you're looking at. So it's not like the thing won't work, but if you want to use the analysis that relies on properties of elliptic curves, you want to be sure that you have an elliptic curve. You need to know that the order of the group of points on the curve modulo this prime divisor P is W smooth. So this is a very inaccessible number, right? You don't know the order of the group of points on this elliptic curve, but you hope for that it's going to be W smooth. And again, W is a parameter that you can adjust when you set up the algorithm. And then, if this is going to work, you need to know that for another divisor of n, different from the one you're looking for, this order of the prime is not divisible by this k. You don't want it to happen by bad luck, that the kp that gets you 0 in one factor also happens to get you 0 in the other factor. So ideally, you'd kind of like the orders of these two groups to be relatively prime, or at least to have the largest prime factor of one be different from the largest prime factor of the other. That's an extremely unlikely event to happen in practice, but nevertheless you have to avoid it. It would be the analog in the P-1 method if it happened that P-1 and Q-1, where those were the two prime factors, were such that the m that you picked was divisible by both of them. And so then, even though the number's composite, you'd get 1 in both factors by Fermat's little theorem. So these are the things that you're trying to avoid. And what Lenstra does in his paper is to try to figure out how likely this situation is to happen in practice. And as I mentioned before, there's a trade-off. You can choose V and W large, meaning that you allow for a large prime factor and relatively large smoothness bound. Then it takes a long time for each elliptic curve. Or you can make those smaller, but try more elliptic curves. Okay? That's basically the trade-off that you get. And the analysis amounts to optimizing that choice. Okay? How do you trade off spending more time on one elliptic curve versus trying more elliptic curves under more favorable conditions? And actually, so this is somewhat of a digression, but when I was in Chicago at UIC, one of my colleagues was Oliver Atkin. He's since passed away, but he was a pioneer in using computers in number theory, and he was at Bletchley Park in World War II working on the decryption of code. He wasn't working on Enigma, but on related codes. And he described his job there. He was like a grad student and a rather junior member of the staff. His job was to sit in a room with a bunch of women who were at hand calculators, and they would do a bunch of calculations trying to break this code. And they had certain rules. If they made progress in a certain amount of time, they took their progress and passed it on to the next hut. They never saw the decryption. They gave it to somebody else to work on. If they failed to make any progress after a certain amount of time, they gave up and they went on to the next message. But there was a boundary, sort of a situation in the middle where they were making progress but not enough progress, and it was a judgment call. Should they abandon that message or work on it some more? And that was Oliver's job. And of course, there's no basis for making this decision. It's just pure gut. And this is a little bit like that, except that Lenstra does bring some science to the business. So what you do is you look at the integers in the range that are less than square root of p away from p plus 1 and are smooth for your smoothness bound. Now, why square root of p and not 2 square root of p? Because after all, the possible orders of the elliptic curve is really between 2 square root of p and minus 2 square root of p from p plus 1. And the reason is because actually, when you look at the distribution of orders of elliptic curves, while it's possible to have outliers closer to the 2 square root of p or minus 2 square root of p, it's much more likely that they land between minus square root of p and square root of p. So if you limit yourself to this region, you know there's a lot of elliptic curves whose orders fall into this region. And so that's really the ones that matter. They get scarcer. And maybe you know that there's a whole competition to try to get as close to that bound as you can. But we're interested in elliptic curves in the mass. So we focus in the middle where the orders of the elliptic curves are concentrated. And we have this hypothesis that the chance that such an order is W smooth is the same as the chance that a random number in that order, in that range, is W smooth. And if U is the number of such numbers, that interval has length 2 square root of p over 2 square, U over 2 square root of p plus 1. So the chance that an elliptic order of an elliptic curve is going to have this property is about U over 2 square root of p plus 1. Those are the smooth ones out of all of them. And our hypothesis is that fraction can be given by just taking numbers of that size. I'm not going to do this whole analysis because it's pretty technical, although it's the analytic number theory which is technical. The elliptic curves part is very accessible, and Lenstra's paper is quite readable, so I suggest that you take a look at it. But what Lenstra proves is that there's an explicit constant c, so that the chance that you're going to succeed at the ECM with parameters v being the size of the prime divisor, w being the smoothness bound, and h being the number of attempts, is this constant to the minus h f of w over log of v, where f of w is the chance that your order happens to be smooth for w. Meanwhile, and the running time for the algorithm is, well, m of n is the time it takes to do these arithmetic operations of size n, so it's kind of irrelevant to this. It's h times w times log v. So remember, we have to compute k times p, and multiplication takes log of k times, and k is a product of powers of primes less than v, and if you go back to the definition of k, you'll see that log k is at most w log of v. So you do it h times. Each time you do it, it takes w log of v arithmetic operations, more or less. That's where this estimate comes from. So you have to trade off. Now, the famous result on smoothness is due to Canfield, Erdős, and Pomerantz. And it says, and this function L of x occurs a lot in computational number theory. And it says that the chance that a random positive integer is x smooth, of size at most x is smooth in terms of this measure, L of x to the alpha, is L of x to the 1 over 2 alpha. That looks kind of a weird way of saying it, but basically what it's saying is, so L of x gets bigger with alpha, and L of x to the 1 over 2 alpha is your probability, and that's the trade-off between alpha and 1 over 2 alpha. I'll show you how this is used in a moment. Notice, by the way, the e to the square root of log x. That's what sub-exponential means. If it were e to the log x, that would be exponential. But we have a little bit better than that, square root of log x. So we have to trade off the probability of success for a given h versus the number of h's that we try. And the running time is h times w, if you go back. And the probability of success is h times f of w. So we want to sort of get the best combination of those parameters, and when you put that together, you have to minimize w over f of w. F of w is the probability that is the number of elliptic curves that have smooth order, and w is the smoothness bound. And if you plug that into this Canfield, Erdős, and Pomerantz thing, you find that the best choice is to choose alpha equals square root of 2. And when you plug that into the running time, you get that the running time is e to the square root of 2 log p. So that's where p is the smallest prime divisor of n. So that's where the running time of the elliptic curve method comes from. That this is the optimum choice, trading off the number of times you try versus the probability of success for any given try. So what do you do in practice? Well, this is now really a science. Well, maybe that's not the right word for it. It's a kind of an art, maybe. So there's a number of things you can do. The first thing you want to do is if you want to do this in practice, is you want your elliptic curve operations to go really, really fast. And that amounts to really analyzing the algebra that you have to do for elliptic curve arithmetic and structuring it in the most efficient possible way, and maybe even choosing the shape of the elliptic curve equation that you use in order to make those operations be really efficient. You can use, the normal Euclidean algorithm for doing modular inversions is very efficient, but for large numbers, there are fast Fourier transform improvements on that and on the arithmetic that you can put in to make those parts of the algorithm more efficient. And you can also make a very careful choice of parameters by sort of looking closely, not just at this Canfield, Erdős, Pomerantz result, which is asymptotic, but using sort of more concrete information that you can get experimentally about the distribution of smooth numbers. And using this, you can make very effective elliptic curve method implementations. And there's some notes from the 2006 Arizona Winter School by Dan Bernstein, which talks about this if you're into that sort of thing. Now, I should say, no matter how thorough you are, there is still a limit to where you're going to get on the elliptic curve method. And so the really huge factorizations that you may hear about periodically, they've done numbers now in the multiple hundreds of digits ranges, are not accessible by the elliptic curve method. And that's where these days people use the number field sieve, which is a whole other completely unrelated approach to this sort of problem. So ECM made some news when it first came out because it, I think, knocked off a couple of the Fermat numbers, but very quickly got stuck. And it was then the quadratic sieve that factored the next Fermat number after that. And if you look back at my little implementation here, so F9 is 2 to the 1024?
512.
Or is it 512? I better use 2 slashes. It's still a pretty sizable number, and if you put this into the elliptic curve method, I mean, it's not going to have any luck because these prime factors are quite large. So, all right, I'm happy to take questions. I think I'm done, and I can put these slides and so forth somewhere, I'm sure. Thanks.